Good afternoon. My name is Ucak-Astarlioglu. I am with Army Corps of Engineers, Engineer Research Development Center. So today's talk, my talk's title is From Experimental Silica Fume Dissolution to Microstructure Modeling and Hydration Kinetics Simulation. So the reason we did this study is we would like to be able to validate and improve our computational simulation capabilities when different types of cementitious materials are in play. And there is always local sources available, but we may not have enough information about making some samples using them. So it would be better if we can compute, if we can simulate what they are going to be. As I said, I am with Engineer Research Development Center, and we are trying to make this world a better and safer world for everyone. And we have 7 laboratories. 4 of them are in Vicksburg, Mississippi, along with the headquarters. So what we have is the Coastal Hydraulics Laboratory, Environmental Laboratory, Geotechnical Structures Lab, that is where I am from, and Information Technology Lab. These are all in Vicksburg. In addition to that, we have Cold Research Laboratory, that's in Hanover, New Hampshire. We have Geospatial Research Laboratory, this is in Alexandria, Virginia, and Construction Engineering Research Laboratory, there is a Kentucky. In addition, we have field officers. And we have national and international partners. These are industrial partners, academic partners. We constantly hire lecturers, masters, PhDs, professionals. So if anybody has any interest, please send them to my way or my colleagues' way. So we go to lab and we figure out the silica fume hydration kinetics. Experimental. We do the experiments, we design the experiments, we go in the lab, isothermal calorimetry we use heavily, we get the result. But the question is, can we really use these experimental data to be able to get some useful simulation results? For example, can we put them into virtual cement and concrete testing laboratory modeling, VCCTL? Or can we put them into thermodynamically assisted microstructure evolution simulator, which is called THAMES? So if we can do that, if we can figure out the particle packing of the silica fume, if we can make this experimental data useful in terms of figuring out the simulation data, this would be a great benefit to us. So that is why we are doing this research. So, what I am showing you right now is 5 different types of silica fume samples we have, and these samples came from Dr. Jedediah Boros' PhD thesis. If you like, you can go online and find his thesis. So he tested all of these in the lab. He did a bunch of different tests on those, and so these samples differed from each other based on the silica weight, percent content, loss of ignition, percent content, and then the surface area. So what I can say is SF2 and SF4 are really similar in terms of the silica content, LOI, and VET values, right? And 6 and 7 are somewhat similar, but SF5 is totally different. The silica content is the lowest on SF5, and the LOI is the highest among all of them. So I am pointing that out because SF5 results did not turn out to be too good. So that takes me to why we are interested in VCCTL and why THAMES. So with VCCTL, we can predict the 3-dimensional microstructure, and we can also predict the cement hydration. Whereas in THAMES, we can interconnect the thermodynamics, the kinetics, the microstructure, all under one model. So THAMES is much more expensive. It requires a lot more modeling efforts, and It requires kinetics data, you need to do the experiment, whatever you want to simulate, you need to get the experimental data first. But with THAMES, we can find out things about other type of cementitious structures, not only Portland cement, but we can go to UHPC, for example. The Army has debated this because it is the compressive strength is 5 to 10 times higher than the regular Portland cement. So actually, THAMES was generated by a Paul Scherrer Institute, and then it's been modified by Jeffrey Bullard's group at Texas A&M. So one of the reasons I mentioned about our partnership with universities and the industry is this is a product of one of those partnerships with Texas A&M. So what Jeffrey Bullard's group did was they simulated saturated or sealed moisture conditions, actually both saturated and sealed moisture conditions. They came up with the empty porosity from the largest capillary pores under sealed conditions, keeping 27% of calcium silica hydrate gel velocity saturated. The remaining was consistent with the chemical shrinkage predicted by the thermodynamic calculations. And with THAMES modifications, prescription of the water-solid ratio of the material is possible without requiring new thermodynamic input files. So THAMES goes to a GEMS library, and it gets the thermodynamic data. And it also uses the microstructure that can be obtained from VCCTL. So here is some experimental and simulation, THAMES simulation results with 20% silica fume. So what we see here is the trends are pretty much similar, right? Experimental trends to THAMES trends are similar. But here you are seeing this green line at the very bottom. It is representing SF5. So we are saying that's fine. So it had the highest LOI and the lowest silica content, the SF5. We go to the 30% silica fume replacement, and again, it is the same thing. This is the lowest, so we are saying fine. We are kind of expecting it. The trends are similar, not perfect, but pretty similar. And then this is important. This is SF2 and SF4, which are called undensified samples, right? So we are comparing the experimental to VCCTL to THAMES in this one, and we are seeing pretty good agreement in between the simulations, both VCCTL and THAMES, to the experimental. For both SF2 and SF4 samples, they were both undensified. And now we move on to SF5 and SF6 samples. On the I forgot to mention, right? So on the X8, we see the time. So our time is day 1, day 3, and day 7. So we have 3 different times. And on the y-axis, we have the normalized heat, which is joules per gram. And SF5 is showing it in THAMES. This is the one that is the dashed line, whereas the dotted line is the VCCTL, and the full line is the experimental. So the VCCTL and the experimental line are in pretty good agreement, whereas the THAMES is showing a similar trend, but there is a bit different. You almost feel like I need a normalization technique. The THAMES model is something to make some to the similar level as SF6 is okay. And there is a better agreement compared to SF5 in 20% silica fume replacement. So this is SF7, it is still showing a good agreement. So when we come to the 30% silica fume replacement, SF2 and SF4, they are all showing good trends, good agreements between the simulated THAMES and VCCTL and experimental. When we come to SF5 is doing even much worse when we have the 30% silica fume replacement. SF6 is showing a similar trend, but definitely the THAMES can use some normalization there. And this is SF7. So the trends are not as perfect as SF2, SF4, but still this is showing somewhat good agreement. So this plus that I am showing you right now is nothing different than I just showed you. These are in just a different way plotted. So on the x-axis, what we see is the experimental results, joules per gram of solid. On the y-axis, we see the simulation data, again joules per gram of solid. So the spheres are showing the THAMES results, and the squares are showing the VCCTL results. If we have the greatest agreement, then you would have expected to see all these dots right on top of this dash, something like this 30-45 degree angle. Pretty much so. I mean, the data points are really clustered around the dash. So these are for the undensified 3%, that's on the left side, and this is undensified 2%. On my side, about the side. So you see, this is undensified 2%. So even 30% is okay, not too bad. So these two are successful, I will say. But when we move on to 20 and 30% SF replacement for the densified samples, which are 20% for the densified samples, we are seeing that the spheres are split from the 35-degree line, right? So they are not showing a perfect line anymore. But you know, we saw that earlier, SF5 is exceptional. The values don't match. But then THAMES is not doing a great job. It is not exactly agreeing like VCCTL and experimental data aggregation. So still need some work for specific types of sample like SF5. So we need another normalization factor, maybe in silica percent rate, I'm thinking. So overall, what I can say is silica fume can be used as a replacement to cement. We were able to establish this through our simulations. Experimental and simulation results showed a reasonable agreement. At least they showed some trends. When you take a look at the VCCTL and THAMES, except for SF5, they showed a good, reasonable trend still. SF5 showed a different behavior because of its physical properties and possibly because of THAMES may need somewhat more modification. And then calcium hydroxide reaction to form CSH gel took place, and CSH gel to nucleate heterogeneity on SF particles took place by formulating them and regressing the experimental reaction data for mixtures of this cement type with the different types of SF. This is another good one. THAMES and VCCTL models can differentiate different types of SFs based on their physical properties, so it's not bad. And the replacement of SF percentage is very important. If you start going up to higher levels like 30%, the trends start getting worse. When we were at 20%, we got much better trends. And then in the future, we'll continue our work. This time, we'll be trying different compositions of materials in cement at various simulation conditions. We will validate microstructure and some other properties, possibly permeability. We will compute pore-shell space ratio to show how calcium silica hydrate binds the material together with optimum amount of additive, and also figure out the linear elastic moduli and transport factor of the microstructure. I would like to thank Texas A&U for their great collaboration in improving the THAMES model from day one to today. They are working on a GUI on this one, and they keep improving the capabilities of this particular model. So at Ördek, I would like to thank Serdar, working heavily on developing this model still. Jedaya for providing the experimental results. And thank you for being here.